every question. So start on Eric.
Yeah, I was wondering about the sort of packaging. So the pictures that we saw at the beginning, you had the MKID detector with this big package around it, and then you had the two outputs. But then later we saw some arrays where they looked closer packed. So with CCDs, the development of large arrays came after you could get these four-side buttable ones. You had the backside readout. So what stage is the MKIDs as far as being able to close pack large arrays?
There are a lot of options, and it really depends on what you're trying to do, what your constraints are. Uh, but there are quite a wide variety of MKID detector designs that are being used now, and you saw a few of them. Uh, the ones that we've been focusing on are essentially direct absorption, where the photons are getting directly absorbed into the superconductor. But you saw examples where antennas are being used first to collect the radiation and then bring it to the MKID. If you're trying to do MKIDs in the visible, you're not going to be using antennas. You're going to be doing direct absorption. But in that case, you really are trying to get your pixels to be a little smaller. If you're working at millimeter or submillimeter wavelengths, your pixels are going to be on the order of a wavelength or a few wavelengths in size. So having a pixel be a millimeter square is no problem for us. That's what we want it to be. But if you're doing visible light MKIDs, that's maybe a little too large. Yeah.
Therefore, the frequency has to be, sorry. Therefore, if the pixels are smaller, the frequency either has to be significantly higher, or you have to put that big monster capacitor, which Mason did. But normally, you're thinking about going from 1 gigahertz to 5 gigahertz for the readout.
So the reason that Ben Mazin's detectors look the way that they do is because of trying to get the pixels to be relatively small, but at the same time trying to keep the resonance frequency in a comfortable range. In that case, it's particularly helpful to be using a material like titanium nitride, which has a very high inductance because it has a high resistivity. And so that helps keep the resonance frequency manageable while shrinking the pixel size down. So there are a number of factors, but in terms of getting the signals in and out, that's actually not such a big challenge. You could always imagine having several tiles in your array side by side, butted together, and simply connect one with another using wire bonds. And so you could imagine accessing everything from the side and having a series of inputs and having some of them actually travel across a few tiles in your mosaic to get to the tile that's being read out. So that's one option. Another option is to go into the third dimension. That's a little more complicated. You start needing to use through holes and so on. But I don't think that this is really going to be a significant limitation. Let me perhaps bring something else up, which I think is an important limitation, which I think potentially there are some solutions to. And I mentioned it briefly in my talk, which is the limits to the multiplexing. Right now, our rough rule of thumb is that the number of detectors we can multiplex in an octave of readout bandwidth is roughly given by the quality factor divided by 100. So if you have a Q of 10 to the fifth, you can have 1,000 detectors per octave, and that simply comes from considering this collision probability and deciding what kind of yield is acceptable to you. And that's where this rule of thumb comes from. But if you really are trying to get much larger arrays, then you would like to have more dense multiplexing. Taking the Q and dividing by 100 means that your efficiency of using the readout spectrum is extremely low. It's in the few percent range. Your resonators are occupying only a small fraction of the readout bandwidth. And so you'd like to have a higher density, but you can't get there with random placement. you have to have some control over the placement. And I think we're starting to see some ideas coming out. Post-fabrication tuning. There was a paper at the low temperature detector workshop in Japan in which the resonances were mapped. The array was warmed up. There was an adjustment done. Basically, the capacitors on every pixel were trimmed based on the map, and then it was cooled again. And that significantly reduced the number of collisions. So with this kind of approach, you could easily see a factor of 10 or more increase in the multiplexing factor. So I think there's good reason to believe that the sizes of arrays will be going up substantially. Right, so the demonstration, the level right now for kids is 1,000 pixels per array has been demonstrated with high yield. An example of that is Space Kids. Our arrays are 500 pixels, but only in half an octave. So the equivalent density is 1,000 pixels per octave, and we're seeing 96% yield. So I think you can look at mux factors at least an order of magnitude higher at some point in the not too distant future, next couple of years, I would say.
So what you have to realize is this is like other technologies. There's going to be a competition because the TES people don't want to give up. Right now they're going brute force and just putting, more wires and more telescopes, right, in order to get more. But the fact is, if you can work it out, you can think about digitally multiplexing, right, so that you no longer send analog signals out of the focal plane at all. That you do complete signal processing in the focal plane, and you only send the digital signals out.
Yeah.
But that's really hard work, but it's conceivable.
Yeah, there's some fundamental limitations to the TS technology that I think will never be overcome. One obvious one is the fact that the squids and the detectors are not integrated on the same wafer. I think the prospects for that ever happening are pretty darn slim because the fabrication is just too challenging. And so that means that you have a lot of wires, a lot of contacts, superconducting contacts required between the detector array and the mux. And that is just a total Achilles heel for the TS technology. It's not only hard to build, but it's a huge opportunity for stray power getting into the detector array or failures. I do not see TSs ever reaching the mux factors that we're getting with kids.
Okay, so I'm going to take the chairman's prerogative and ask my own question, and that is about quantum efficiency. So, yesterday everybody nodded their head, glibly when I, showed that my telescope would be significantly more sensitive than a telescope in space, the ultraviolet optical telescope on Swift. The reason is that the ultraviolet optical telescope on Swift used a microchannel plate, which has horrible quantum efficiency, and it's all where you don't want it in the ultraviolet. So I'm a big fan of quantum efficiency. So I'm probably way behind the curve because I've read Muzin's very old papers, but in that there was very low quantum efficiency. And so I'd like to ask you to go all the way from the millimeter all the way through all the kids you know of, and let us know what the quantum efficiency is now at best, and where you think that's going to go, and how we're going to fix it.
So, in terms of millimeter, submillimeter, or far infrared detectors, it's quite easy to design the detector. Am I on or off?
I think you have to put it right up to your lips. And I also forgot to ask, when you do quantum efficiency, compare to the next best detector.
Can you hear me now? Okay. So I'd say there's no particular challenge in achieving very high efficiency at millimeter, submillimeter, or far infrared wavelengths, and there's no particular distinction that you could draw between kids or some other technology. If you're talking about direct absorption, it's a question of impedance matching to the wave. If you're talking about antenna coupling, it's a question of the detector design and how you terminate the transmission line at the end of the antenna. And there's really no difference between how this is done with a kit or how it's done with some other detector. And it's straightforward to achieve high efficiency with good design. So I think there's not much difference between technologies at those wavelengths. As you go shorter, especially if you're thinking about infrared or visible light detectors, the quantum efficiency is controlled by the material that you're using. So if you tried to make a visible light kinetic inductance detector using aluminum, which is a very nice superconductor, it would be a terrible detector because you can make good mirrors out of aluminum, not good absorbers. So that's one of the reasons that titanium nitride is being used for Ben-Mezine's detectors. And if you look at the films, you can tell they're reasonable absorbers because they're not shiny like aluminum. They've got a gold tinge, so you know that they're absorbing. But the absorption as a function of wavelength is controlled by the material, and there isn't much you can do except changing materials to change its absorption properties. There may be some things you can put overlayers on. Ben has had various ideas of trying to put some kind of additional material to serve as the absorber, but none of this yet, I think, has really been demonstrated. So there, I think you're really talking about looking at materials. Having said that, the absorption efficiency for titanium nitride isn't so bad. It depends on the wavelength, but it can be 40 or 50% in the visible range. I think as you start going towards longer wavelengths, it becomes a little worse. So that's the real issue. It's a materials issue.
Tajima, so you're saying everything in the submillimeter will be near 100%.
I think you could design it based on your needs. You could design it to be, quite high, and how high you get, I think, is, depends on the effort you put into the design. The more effort, the better it'll be.
Tajima, what is your actual effective quantum efficiency?
Recently, we are trying to make a multi-band detector. So for that case, so for the case of multi-band detector, so we haven't reached up to 70% yet. Maybe somewhere around 40% or something like that.
One of the issues for the antenna coupled detectors in terms of quantum efficiency has to do with propagation loss between the antenna and the detector. There's, as you saw in the diagrams, there are superconducting transmission lines that are being used to bring the radiation from the antenna to the detector. And I think, as you saw in the example of Groundbird, there's a variety of components that are being used to combine the various feeds and to get the right polarization onto the detector. That path from the antenna to the detector can be lossy, even though you're using superconductors. And the losses primarily, I think, people would agree, come not from the superconductor, but come from the dielectric. So this is a particular issue for detectors of the kind that are used in the BICEP series of experiments, which are using these fairly large phased array antennas in which the path length along the superconducting transmission line is longer. And in those cases, they're particularly exposed to the dielectric losses and are achieving efficiencies of 50 or so %. But it's largely limited by the dielectric. It's not the detector itself. It's some other material that's being used as the dielectric.
Are there any other questions? Because otherwise you'll have to listen to my questions some more. There is kind of a conducting structure in the optical M kits that has a direction. There are lenslets over it, but is there any way you could think of using that to make a built-in optical polarization? If you made this detector that has an inherent property that stays stable, that's can be better in a lot of ways than having a rotating half-wave plate in front of it,
So that's an interesting possibility. It's easy to do in the millimeter submillimeter. In fact, the simple kinds of meanders that I showed are linearly polarized. And to get a structure which absorbs in both polarizations efficiently requires a little more effort, but is possible to do. I showed another example that absorbs both polarizations. But to do the same kind of trick in the visible is considerably harder, because what you need to do is to reduce the line width and the pitch so that it's a fraction of a visible light wavelength. That structure can act like a diffraction grating. And to stop it from acting like a diffraction grating, the pitch, the spacing between the wires has to be sub-wavelength. And so if you have very good lithography, electron beam lithography is an example, you could make a structure that would be linearly polarized. And in fact, there are papers in which lithograph polarizers have been demonstrated using aluminum as an example. So it's physically possible to make the structures at the scales required. So I think in principle you could make a single polarization optical M kit, but it requires quite good lithography. You need to have a group that's quite skilled with electron beam lithography.
Can I ask? You had talked about photoristography. Can you explain what the difference is?
Do you mean the aligner and the stepper, those two
Can
different?
you put the microphone closer because we can't hear you?
Do you mean the photolithography based on aligner and the stepper?
Right. On some of your slides, you were talking about.
Oh yes.
Yeah.
So there are two technology for the
Very
photolithography.
close. Very close.
There are So there are two photolithography technique technology. So one is aligner. So aligner can make a photolithography for the large area. And the stepper, on the other hand, so we can make a fine structure, but the spot area is very small. So for the case of large array for the M kits, so of course the many M kits are connected by using a single feed line cable. So aligner is a good choice for to make such structure, as well as a resonator structure. On the other hand, for the antenna structure, so it's higher frequency than the case of the M-kit resonance. So that's why we need a fine structure. So that's the reason we choose a stepper to making antenna components.
To give you a rough feeling, the aligner will be good for structures of order a micron or so and larger. The stepper, which uses a deep UV excimer laser, 220 nanometers typically, depending on the model, can get you down to maybe 150 nanometer resolution. So you can make line widths of order 150 nanometers with the stepper, but not smaller. And that's not good enough if you're trying to get the single polarization optical detector. Now, industry can make 14 nanometer transistors using more or less optical lithography, but they have billions of dollars available at their disposal, whereas research groups tend not to have that. And so for us to make lines significantly less than, let's say, 150 nanometers, you have to move to electron beam lithography. You can get down to 10 nanometers or so, 20 nanometers with electron beam lithography. So it gives you a sense of what's possible.
Okay, so slight change of topic. Sensitive detectors are great, but not if they're just detecting noise. So when we observe from the ground, obviously you worry about water vapor, for example. For infrared detectors, you're worrying about all the OH lines and so forth. Are there techniques for observing basically between the OH lines, absorbing the OH lines? I've heard of these things called ring resonators, for example, which will knock out lines. For CCDs, people are working on germanium CCDs to push further into the infrared. What's the sort of landscape that we can expect for those sort of advances?
To be honest, since I don't work at visible or near infrared wavelengths, I don't remember the spectral width of those OH features that you would like to avoid. But if your detector had good enough energy resolution, you could imagine simply discarding those events that corresponded to those features. Technically, this might be pretty challenging. You'd have to go and look at how sharp those features are. My guess is it's probably not in the cards anytime soon to be able to do this, but it's something to think about. In terms of longer wavelengths, there you're not using the energy resolution of the detector. You have a filter ahead of the detector, and you're solving the problem in exactly the same way as you would with any other kind of detector. Your detectors have to reach the photon noise limit, but once you've done that, you're there.
George, for Pixie, are people thinking of MKIDs or not?
I don't think that they are. I think Pixie has been, designed based on assuming it's a polarimeter that, it's a bolometer, polarimeter, interferometer, and I don't think they have been considering MKIDs as a possible instrument. It's true they probably should think about it, but I don't think it's in the set of people who are pushing this. I don't think it's in their technical background to do that. And so one of the things that people should be bearing in mind is that when you're talking about doing what Groundbird is doing or whatever else is going on, you're talking about needing to measure 10 to the 14th photons per pixel, right, in order to get down to the sensitivity level we're talking about. And if you ask how many photons come in per second for the whole CMB, it's only 10 to the 12th. If you detected every CMB photon that came in your antenna, right, with a wavelength of 1 centimeter or shorter, you would only get 10 to the 12th a second. So you have to go to a large number of pixels. You have to have high quantum efficiency. You have to be observing a long time. And so, Groundbird barely is able to get to the sensitivity level they're talking about if they're close to quantum efficiency. That's the kind of thing. So when you're talking about the development of detectors, you have to realize how far detectors have come in the CMB field and how hard people are pushing them now, and that the only solution that we've had is essentially multiplex. And that's why, Jonas is, prejudice that multiplexing the TES is going to be a fundamental problem is relevant, right? Because in order to think about doing the next generation properly, you're going to need to go to 100,000 or a million detectors. and that's a really serious problem. Right? 100,000 is the absolute lower limit of how many detectors you need, because as soon as you start saying, I can't take every CMB photon because I have all this galactic background, and so I have to take these narrow windows, you're suddenly cut off the number of photons you can have quite a lot. And the reason people went to bolometers at the shorter wavelengths was because they could take many modes, right? Because the number of photons per mode is approaching 1, and so forth. So being forced by the backgrounds to narrow the bandwidth and have more selected bandwidth, but so you're making this trade-off, right? And so the question is, what's the right approach? And the answer is, we've been pushing the detectors very hard, and it's got to be the same problem as the maintaining the I forgot the name of the law, Moore's law. So I should remember Moore's law. Maintaining Moore's law for computers has gone to the fact that you're sitting there with computers that have multiple processors in them, because it was harder to make a processor that was smaller and faster than it was to just put multiple processors in your laptop. The same thing is true for detectors, but we're approaching the quantum limit. So you can say, well, it's a quantum limit or not. The answer is no. You're probably a factor of 3 or 4 away from the quantum limit, but it's already easier to go to more detectors. Even if you get to the quantum limit, you're still going to have to go up by order of magnitude for more detectors. That's why when you look at CMBS4, there really has to be 100,000 to 1 million detectors for them to achieve the science goals that they want to. You're literally down to counting photons. You wish you were there already, but the best you can do is count photons, and you're almost counting photons. So the detectors in the millimeter wave are going to get only another factor 2 better, and then you're going to be going to huge array. All the progress is going to be in doing huge arrays and multiple readouts, and that's why the issue of do you do it at 1 gigahertz or do you do it at 5 gigahertz is relevant. And you probably do the millimeter wave at 1 gigahertz because it's possible. But when you're getting to the infrared and optical, you're probably going to have to go to 5 gigahertz or 10 gigahertz to do that. And so improvements in detectors have driven astrophysics for a very long time, just the way they've driven computer stuff. Now we're being forced to think of new technologies, right? So the thing that we didn't point out here is that computers are reaching their limit, and Moore's law is going to reach a fundamental limit, just like the CMB detectors. Moore's law is going to reach a fundamental limit that you can't make your gate width less than an atom, right? So we're down to a few hundred atoms now, and so you can treat it as a bulk device, but soon you won't be able to treat it as a bulk device. It'll have to be. We're going to get quantum computers one way or another, right? Either by having transistors being quantum, or more likely that way. And that's why the second reason that kids are very interesting is they're probably one of the most likely devices to be a quantum computing device. And it has to do with the fact that we're working out, to get to the quantum limit, we're working out how does a single photon interact with a single quantum state in a device. Now, we're not doing that yet, but we're heading in that direction.
This is a good time maybe to say give a couple of stories. Since you were talking about Moore's law, I had to serve.
There's 4 Moore's law.
Yeah, I had to serve as a tour guide in around 2000 at the Submillimeter Observatory in Hawaii when the Caltech Board of Trustees came to visit, and they were alternating between visiting the Keck telescopes and visiting our Submillimeter telescope. And so a group came through, which included our president, David Baltimore at the time, and I was showing them an instrument that was on the telescope that had 20 pixels, and we were very happy to have 20 pixels on the telescope. And I told them that the 1 pixel instrument that we had when I started as an assistant professor had been retired, but then off into the wings in the lab was an instrument with 144 pixels that was getting ready for its first test on the observatory and how exciting it was to have 144 pixels coming. And so our president turned to his group and said, "So is that doubling about every couple of years?" And standing right next to him was Gordon Moore. So we have plots like this that basically start around 1990 that show the number of pixels in an array as a function of time, and it is exponential. And it's for the reason exactly that George mentioned, which is once you get to the point where your detectors are not limited by detector noise, but are limited by photon noise, the only way to keep doing better is to have more and more of them. And for ground-based work, right around 1990 is when that shift really started to happen. And that's driven all the development of all of these multiplexing techniques. For many years, the game was to simply get a better detector. That game was over.
Right. And so if you look, there is a Moore's law for the CMB detectors, and that has been through, I forget how many doublings, but it's quite a lot. And it's really since 1990. It's actually started before 1990, but the doubling has been about every 2 years.
There's another kind of law you can draw, which is detection speed, which brings in the detector sensitivity as well as the detector count. And I think Paul Richards used to make this plot, and if you make that plot, it'll go back at least to 1960 with more or less a straight line going up exponentially.
So we have been used all our lives to technology moving at a very rapid pace, and we're facing what the Moore's law in computation is facing. We're facing that Moore's law in the different versions of stuff, but that we're facing a fundamental physics limit, and you're going to have to change technologies in order to stay on that curve. And that's probably true, but we don't know what new detector technology could come along. Whereas at least in computing, we know computation physics. But the fourth Moore's law is the price of the factory doubles every time. So that now, every time Intel has to make a new chip, they bet the company. And so what you've seen is they fail to bet the company lately. And because of that, they're the number 2 chip maker in the world because Samsung just passed them. And the issue is the same thing is true for some of these experiments we're doing. The cost of the experiment is going to be doubling every so often, but it won't be every 2 years. But look at the cost of CMBS4. You'll realize the scaling from the early CMB experiments to now.
One of the things that makes MKID's work is the real Moore's law. We're using the fact that digital signal processing has become very cheap. So calculating these FFTs at some ridiculous rate is no problem anymore. But one of the issues that we have is power consumption. It's not so much a problem for ground-based instruments. For space instruments, it's a much more serious problem. And we're thinking of concepts where we have hundreds of thousands of detectors on spacecraft, and trying to figure out how to read them out is a real challenge. So that's one reason why getting to higher multiplexing density is going to be particularly important, because not only is filling up only a few percent of your readout bandwidth with pixels, it's not only wasteful in terms of bandwidth, but it's wasteful in terms of power consumption, because you're doing all that signal processing anyway. So getting higher multiplexing density is important for that reason.
So one of the things that you shouldn't forget is that not only have people been focusing in the CMB because of excitement, but the fact is it's natural to start at low frequencies where the physics and the electrical engineering so much is easier. But these devices will migrate up and particularly eventually come to the infrared and the optical. And they should revolutionize the infrared and the optical unless there's some fundamental limit. That's why I asked you is there some limit why you can't get the R factor up to, once you get to the one, the R factor of 100, you basically are not going to do these filter band measurements anymore. You're going to use optical MKIDs to do these measurements, and that's the question: is there something that blocks that future development?
So there's an interesting history in terms of X-ray calorimeters and the energy resolution that they've been able to achieve, and it's come gradually with a lot of effort and a lot of different types of detectors being tried, and eventually a few of them working better than others. But again, the whole history there is understanding where the energy is going and making sure that energy isn't escaping or isn't getting trapped somewhere. So there's a fair amount of detailed physics that goes into that. That's the kind of work, I think, that you're looking at to get to very high energy resolution optical methods. Is really understanding the physics of what's happening with the energy, photon energy in the material.
So I guess we're gonna. I want to change direction one last time. We're getting toward the end. So, what do you think is the high energy limit for MKIDs? And so can you make me a 5 centimeter deep pixel to give me some 500 keV photons, because I would love that.
So if you're trying to do high energy detection, the strategy is to split up the problem into absorption and then detection, and not try to do it simultaneously. So obviously your range of your 100 keV or whatever photon in your superconducting material becomes very long, and the superconducting volume becomes too large to make a sensitive detector. So you simply absorb the photon in the substrate, for instance silicon, and then you capture the phonon energy that's deposited in your superconductor. And so detectors like this have been made and tested; they work. So there are ways to do this.
You lose most of the advantage most of the advantage of MKIDs by doing that.
But you have to look at the ultimate spectral resolution, energy resolution that you're trying to get to. But there's no reason why with a properly designed device you couldn't capture most of the phonon energy into the superconductor. The phonon energy in the silicon has nowhere to go. The mean free paths for the phonons are incredibly long. Processes like anharmonic down conversion are extremely slow. So if you can make it so that your superconductor is the only place that phonon energy can go, you can have a pretty good device.
And then you can have the readout advantage.
Right. So that's what I think about it is, at a certain point, MKIDs and microbolometers are indistinguishable. If you separate the factors, if you absorb the photon in something that conserves the energy, and you couple it to the KIDs, then the KID is a temperature. It's reading the total energy deposited, right? Just like the microbolometer is temperature change. And so you do it here by counting pairs of electrons, right? And so it's just a readout question. It's the same technique. You're saying, how can I determine how much energy was deposited when this photon came? The thing that you want to do is you would love to have sufficiently high time resolution that you could count individual photons. And that's what we're talking about, and that's why suddenly it becomes relevant to ask the astronomical site, what's your sky look like? Because a bright sky kills you.
So something that your student Chang needs to learn. If there are no more questions, I'm going to officially declare this session closed 3 minutes early, and we get to lunch 3 minutes early.
Oh, we have a talk.
We have a talk.
We come back.
Sorry.
It seems like there's
let's see.
I may be mistaken.
Sorry, 1150 acousto-optical correlator. Is Abdulkan Umbentov here? Okay, we thought he was. We did think he was here. So if you could just give us a minute, or if someone could call Aliyah and ask real quick where he is. Anyone has her phone number handy?
So how come you didn't talk about silicon photovoltaics?
Yeah, so you have to teach your student about dark current and about backgrounds.
That's true for everything. The silicon has a fiercer temperature. Well, maybe not a fiercer temperature. So, for Jonas, this might be interesting. So, one of the things that I've been having a student work with to talk about having the people here be the first people to use the silicon photomultiplier. And it turns out we're working with Hamamatsu. Hamamatsu has been the pioneer, they make phototubes like crazy. And they now make a silicon photomultiplier tube, which they don't sell yet, but they make it. But they're making a prototype for a positron emission tomography camera, and they sell an array of 4 8x8 silicon phototubes, so 16 by 6, 256 channels, and they claim the quantum efficiency is fairly high. So this is the other extreme case where you count individual photons, but you have no idea the energy. But so that is an area where we're talking about. No. People here in Kazakhstan use the telescope, the gamma ray burst telescope, which is sitting waiting for a gamma ray burst to look at the sky or look at objects in the sky with a silicon photomultiplier tube and see
No, because we have
how well it might do. So this is kind of an experiment because it allows you to do the fast astronomy. So before I was looking at the multi-anode, the Hamamatsu multi-anode phototubes as a way to get reasonable amount of sky coverage and so forth. And so that has to do with the fact that motivated that radio astronomers could have discovered fast radio bursts decades earlier, but nobody looked. Right? And now we know they're there. We know they're cosmological. And so, I was pointing out to Eric that the fast radio bursts are one of the few independent ways we have of showing there is an intergalactic medium that actually has in it almost all the baryons. Most of the baryons in the universe are not in galaxies. Most of them are in the intergalactic medium or in the intercluster medium. And you can, by doing the dispersion measure because these radio pulses are so narrow, you can actually measure the electrons, the number of electrons on the line of sight, the emission measure, and you see large numbers, right? And you put in estimated distances as a record. And you find that it's very close to the density, the Big Bang nucleosynthesis value. So we have evidence that there really is this intergalactic medium at the right level.
To be the effective.
Well, no, it's the stuff that I just looked at. I can pull it up for you. It's within 12%.
But based on because we only know the distance to one of the
Right. Well, you have to estimate some of the others for various ways. Right. Exactly. So it's early. So I'm prejudging, but when we get these wide field of view cameras online, or radio cameras, then we will see many per day, and then you'll know fairly quickly. Right? Is he giving the talk or not?
Marjan, a question here.
Thank you so much. Yes, so thank you so much for the presentation. I had questions regarding your detector. What was the resonance frequency of your detector, and what factors did you consider when choosing that frequency? And second question is, did you use micro lens or feed horn arrays for your detectors? Oh, no, it was for you.
So we have worked with a wide variety of detector designs, but most recently the detectors we've been working with have resonance frequencies that are fairly low at about 1 to 200 megahertz, and that's intentional because the number of resonators you can multiplex per octave is not really dependent very strongly on which octave you choose. So if you work at 100 megahertz, 100 to 200 megahertz, you only have to read out 100 megahertz of bandwidth to get your 1,000 detectors. If you choose to do this at 4 to 8 gigahertz, now you have to read out 4 gigahertz of bandwidth. So it's much more demanding in terms of the electronics. So we very much prefer reducing the resonance frequency as much as possible to save on the electronics task, the readout electronics. In terms of coupling, the most recent detectors are using microlens arrays, although we have other types that use waveguide horns. We have types that use antennas, I think of the kind that you saw for ground bird behind the lenses. So we've tried a number of different things.
Yeah, and Osamu, could you also respond to that question?
So for our choice for the resonant frequency is around 4 to 5 gigahertz. So
500 gigahertz?
4 to 5 gigahertz.
4 to 5 gigahertz.
Yes. So actually, there is no deep reason to choose that frequency because we just follow the pioneers, you know. And another reason we use that frequency range is most of the parts, for example, called RNA, low noise amplifier is good has good performance and not so expensive because of the development for the Wi-Fi, for example.
One thing I should add, since you mentioned amplifiers, is that our shift down to these lower frequencies occurred when we could get very low noise silicon germanium heterojunction bipolar transistor amplifiers. So we have a group in electrical engineering, Sandy Weinreb, that helped develop this. And once we were able to get our hands on these amplifiers, it made a lot of sense to go to these lower frequencies.
Okay, Alia, do you want to make some announcements? Why don't you grab a microphone or grab mine?
Now we're at lunchtime beginning right now, so you're free. Lunchtime is beginning right now, and you are free, and you can use the midpoint here or some another place in Nazarbayev University. And I would like to announce about the tomorrow session. So tomorrow in August, the expo session will be at the Congress Center, at the Expo Center. So the bus will be leave from Radisson Hotel at 8:15 a.m. and go to Congress Center.
That's all of us?
Yes, all of us.
There's some of us are on the panel.
Okay. Yes, I know. Your panel will start at 9 a.m. So you can, if you would like earlier, so you can. So also, if you would like to participate in this session, please make registration and contact Uchigis, but not include invite. All our invited speakers are registered already. Have already agreed. I mean, talk about another participants. If you'd like to participate, you please make registration, and Chingis will help you in this with registration. So, and the second one is that today will be the banquet at Marriott Hotel, and our bus will wait at 6:45 here, and will drive us to Marriott, and then our invited speakers for Marriott will drive it to Radisson Hotel. So, and that's it. That's it. If you have any questions, please. Okay.
So the next session starts. So 1:15 is when we start with the talks again.